Assalamualaikum warahmatullahi wabarakatuh. Boleh dengar?
Dengar, Prof.
Okay. Bismillahirrahmanirrahim. So today is 24th of January, Sunday. So we continue with our second case study, chapter 5C, case study using industrial hydraulic actuator system. So let me maximize. Okay. So in this outline, I will give some theories on the system ID, then model identifications using MATLAB, some feedback control system design and simulations using Simulink. So as you know that in system ID, we derive the mathematical model based on the input-output measurements for a certain system dynamic. And this required design and implementing high performance control system. That's why we need to obtain the model, okay, need to be validated to verify its preciseness before it can be used. So we compare, in validation, we compare the output, obtained model, and the output of the plant, meaning that like yesterday, we compare between the measured and simulated. Okay, measured is real, simulated is estimation. We follow the procedure, okay, the four main procedure: experimental setup, model structure selections, model estimations, and model validations, with the closed loop based on the best fit, based on the minimum MSE, minimum FPE, and so on. So the process can be tabulate more detail in the block diagram based on follow, okay, lebih kurang sama macam yang ini, okay, cuma dalam bentuk yang berlainan. So we already know that to estimate the model, we need to have the comparison between the actual Y and the estimated Y, because the difference between the actual Y and the estimated Y, the output, will give you an error. Okay, the minimum, the error, the good is the adaptations of the parameter algorithms for the estimated model parameters. That's why we have a model structure based on general linear parametric model, with Y is the output, U is the input, okay? And we have a polynomial A and polynomial B that represents the coefficients, okay, the order of the systems, where D is the time delay and A is the number of poles and B is the number of zeros. U, Y, and E is the input, output, and noise respectively. So I also introduced to you a few models in the chapter 3, where we know that ARX model, auto-regressive with exogenous input like yesterday, and then auto-regressive moving average with exogenous input RMAX model, when the signal to noise ratio is small. So we use RMAX model, but if the SNR is high, the signal is more significant compared to the noise, so we use ARX model. Then we also introduce output error model and Box-Jenkill model based on the certain applications. So ARX model is the basic model for all models, informing a few other model structures. Okay, it's represented by the equation A equal to B plus C multiplied by E. A multiplied by the output, B multiplied by the input, and C multiplied by the error. We also have OE models, okay, based on the equation Y is equal to B divided by F multiplied by U plus the noise. And also Box and Jenkins model. All of this is based on the general parametric models that represent by this equation, okay, where where A multiplied by Y is equal to B divided by F multiplied by U plus C over D multiplied by E. So input signals is the most important things, the signals that will tube inside the system. Okay, so good parameters identification require the usage of input signals that are rich in frequencies. We are using two methods, which is PRBS, which can be generated using a square pulse, but to implement it in a hydraulic actuator is a little bit difficult. Okay, because hydraulic actuator is a dynamic system, it's moving. Okay, it's a moving system compared to hot air blower. Hot air blower is more static process. Okay, it's not moving, so the process is there, right? So using a sinusoidal signals by the formula of U is equal to lambda, sigma A multiplied by cos omega I Tk, where A is the amplitude, W is the frequency, and Ts is the sampling time. So we have a capital P, which is equal to N divided by 2. Okay, so N divided by 2, N is the number of parameter that needs to be identified. If P is equal to 3, capital P is equal to 3, so we have about 6 model parameters can be obtained, okay, by using input signal U is equal to A1 cos plus A2 cos plus A3 cos. So derived from the measured input-output signals of a real plant that needs to be identified, that is the plant model. Okay, so we use the ARX parametric model structure in this today's demonstration due to the simple structure and represented by a simple linear difference equations. So by assuming noise is zero, almost zero, due to the fact that signal to noise ratio is high or significant, so we obtain this equation y plus a1y, k minus 1, and so on, where the NA, the order of the NA is higher than NB. That's why we get a transfer function for the ARX model, y divided by u, okay, equal to b divided by a. As I showed you yesterday, by clicking the model output in the system ID toolbox GUI, we can obtain the B parametric model and A parametric model. So minimum phase model can be obtained using a large value of sampling time, while a non-minimum phase model can be obtained using a small value sampling time. This is proved by Estrom and Wittenmark in the book 1987 and Soderstrom and Stoica in 1989. We will verify the slide number 15, okay, by using a data from the real experiment, okay. This slide number 15, minimum phase model and non-minimum phase model. So what is the difference between minimum phase and non-minimum phase? Yesterday, I told you that when the zeros is outside the unit circle, the system is non-minimum phase. But if the zeros is inside, all are inside the unit circle, so the system is a minimum phase. So the definition is a non-minimum phase transfer function has zeros in the right S-plane. This is S-plane in continuous time. The one that I mentioned yesterday was in the Z-plane. S-plane, there is no unity circles. But in Z-plane, there is a unity circles. One is continuous. Yesterday was the discrete form. Okay, so Z-plane correspond to the discrete form, digital control, and S-plane is referred to the continuous time. So non-minimum phase transfer function has zero on the right S-plane, while minimum phase all zero lie on the left hand S-plane. So it can be shown here. You have two figures. Okay, so left figures is the minimum phase, while the on the right is a non-minimum phase, due to the fact that there is a zero on the right S plane. Okay, so this is S plane, J omega versus real. And in the phase form, you can see that the phase diagram or the boat plot phase diagram is shown here, where non-minimum phase is the blue line, starting from 180 degrees, then slowly decreasing to 0 degrees. But for minimum phase is represented by the black line, start from the 0 degrees up to 80 degrees and go back to the 0 degrees. The difference between the minimum phase and non-minimum phase transfer function using a phase boat plot. So for parametric model identification algorithms, we are using a recursive least square. So I didn't teach you recursive least square is more longer calculations compared to the generalized least square. So I only teach you simple least square and generalized least square. And recursive least square can be referred to other books which you need a computer program, okay, because the process is longer than the generalized least square. Okay, so in generalized least square, we start the simple least square, we use the A value that we get, we insert inside the filtered algorithm, then we got generalized least square. And recursive is longer than that, okay, so it will be longer, but it's good if we have time to calculate it, okay. For example, for research project, for master by course, okay, so we can do the program. In fact, the program already available, okay, in the MATLAB. If you type recursive least square algorithm programming, so you can get from the Google, okay. There is a lot of forum discussion on this recursive least square algorithm. So it uses a regression vector, so don't worry about the equations, okay. This is just correspond to the recursive least square algorithm. We have a regression vector, then we have an approximate parameter vector. Then we have a predicted error to compare between the current value and the next value. Then we have the update approximation subroutine to calculate the estimated value. Then we have the correcting factor. Okay, so correcting factor is a number that compensates the value of the parameters. So it will give some effects of errors due to truncation and runoff during a computational of covariance matrix, and this can be improved by using a UD factorization method, okay, which is fast convergence, effectiveness, and symmetry of PK. So for slide 19, for slide 20 and 21, you don't have to worry about it, just a knowledge on the recursive least square only. So there is some modifications using the correcting vector, using the UD factorization algorithm to estimate the parameters. That's why in model validations, once we got the mathematical model, so we will use it several tools to measure the error. For example, yesterday in the system ID toolbox, there is a FPE and MSE. FPE is the final prediction error, which is this one, okay, Akaiki's final prediction error. And MSE is mean squared error. And we also have another one criteria is Akaiki's information criteria. Also can be used, and the popular one is of course best fit, okay, introduced by Leonard Jung in 2002. So this criterion show the preciseness of the approximate model as compared to the true model. So what is a final prediction error yesterday? So the formula is given by FPE is equal to V1 plus D divided by N, and divide by 1 minus D divided by N. Okay, so V is the loss function, D is the number of approximated parameters, and n is the number of samples. Therefore, V is equal to E squared divided by N, and E transpose multiplied by E divided by N, where EK is the error vector. So the calculation is based on the value of the FPE. Usually is almost 0, then the model will be accepted. Second one is the AIC, or we call it as the Akaikis information criteria. AIC is equal to log V multiplied by 1 plus 2D divided by N. Okay. Then this selection of model usually based the value of the definition is the same, B, D, and capital N, but is using a log value. Okay. So the minimum it is the almost 0 that is accepted, and the model can be used. How about the best fitting criteria? Best fit criteria is based on the percentage formula 100 minus 100 multiply 1 minus normalized y cap estimated y minus y divided by normalized actual y divided by y mean. Y mean is the mean value, okay, the mean value of the output. Y cap is the approximate value, and y is the true value. All are based on the output value. So model selection will be based on the highest percentage value. Ideal is 100%. Acceptance is 90% and above. So this is the plan of the industrial standard hydraulic actuator that used in the laboratory. So we have a positional transducer, or usually known as the LVDT, linear variable differential transformer, that convert the displacement in millimeter to equivalent voltage. Okay, so displacement is the physical signals in millimeter, jarak lah, distance. Then LVDT will detect and convert this displacement to the equivalent voltage. And then we have a bidirectional cylinder, which we have a piston, which is moving forward and backward. Okay, and then of course we have a proportional valve. The valve will control the flow of the liquid in this piping, the black piping, inlet and outlet. So the description of the plant is using a hydraulic actuator, Novotechnic, brand Novotechnic, have a piston 25 mm, piston rod 16 mm, and the stroke is 400 mm. Stroke meaning the maximum piston it can go about 40 centimeter forward, then 40 centimeter backward. Okay, 1 centimeter is 10 millimeters, so maximum is 40 centimeter, which is equivalent to 400 mm. Okay, it have a position transducer, which is a LVDT, and of course to create pressure in the oil, we use a pump. Okay, pressurized fluid flow, controlled by electronic control valve, which is the P controller. Okay, and of course we have to give a voltage plus minus 10 volt DC with the current 4 to 20 milliamp. Okay, for the pump and for the control valve. So this is the focus up on the pump, and the what do you call this, a controller. Okay, a servo valve, and the pump motor that pump the oil inside this reservoir, the black reservoir. Okay, and there is a meter to calculate the pressure. And then this is the cylinder with the LVDT. So this is cylinder, and this is the LVDT. Okay, linear variable differential transformer that sit side by side with the cylinder. And if we don't have a LVDT, we also can use a drag wire sensor. So drag wire sensor is similar like LVDT. We call it as a drag wire sensor. That this wire will be dragged by the piston forward and backward. and the displacement will be measured, will be detected by this drag wire and convert to the voltage value. Of course, we need a computer, okay, and oscilloscope in order to capture the data that during the experiment. So I show you a movie, okay. Tengok movie, boleh tak? Boleh tengok movie?
Boleh bro.
Eksperimen dia. Nampak?
Nampak.
Okay, so that is the movie. Okay, nampak movie-nya? Macam mana kita buat the experiment? Okay, we have a big industrial hydraulic actuator. Okay, with the liquid, oil liquid. Okay, pressure high liquid, oil liquid, moving from inlet to outlet, and then move the piston back forward and backward. Okay, so usually used in the robotics lah. Okay, or any other application that using a hydraulic actuator, for example, aeronautic industrial, kapal terbang dan sebagainya. So first kita nampak tadi dekat scope dia ada macam sine wave kan. Dekat scope pada input and output, that is due to the input signal. Okay, so we generate 3 different frequencies, which is V in is equal to cos 0.5 TSK plus cos 2 TSK plus cos 5 TSK with the sampling time TS. Then using 3 different frequencies for the input signals. Why? Because simply models order obtain limited to second and third order only. Because we read a book, yes, it is a third order maximum for hydraulic actuator. And higher order might produce inaccurate model or unstable output. Okay, and then the third order model will represent the nearest model of the true plant. So this is the input signals that we generate, right? And then I give you a few file, which is model A, model B, and model C dalam WhatsApp. Dapat tak? Dapat tak?
Dapat bro, dapat.
Kita letak dekat desktop. Kita, you boleh play around lah. This saya demo kan, cara nak pakai. So ada 3 model. Okay, model A is sampling at 45 millisecond. Kita nak tengok dia punya kesan dia bila kita gunakan lower sampling and higher sampling. So kita ada 3 model. Model A sampling data sampling at 45 millisecond. Model B sampling at 50 millisecond and model C is sampling at 55 millisecond. Okay, so for model A, as usual, kita pakai system ID toolbox. We have about 1,000 samples. The first 500 for estimation. The remaining 500 is for the validations, okay, as shown here. The input and output ditunjukkan di sini, okay. This is your input signal with 3 frequencies, and this is the output signals. Then we use a system ID toolbox, so we obtain the what do you call this? The ARX model, okay. Apa tak boleh pakai ni? Okay, so polynomial B and polynomial A. Okay, so polynomial B kuasa 3, polynomial A kuasa 3, but polynomial B can be factorized. Okay, so 0.1487 Z letak depan, then multiply by 1 plus 1.09 minus 0.44. Okay, so kita lihat di sini numerator ni bila equal to 0, so kita akan dapat 2 zeros. Dan denominator ni kalau equal to 0, kita akan dapat 3 poles. Okay, so dia jadi macam ini. Okay, so kita factorize. The value of 0 is minus 1.4 and positive 0.3. Jadi yang minus 1.4 is outside unit circle. Yang positive 0.3 is inside unit circles. Okay, but poles semuanya 1 minus 0.4, okay, minus 0.4 and 0.377, all poles is inside the unit circle. Okay, then we do the validations. Okay, so kita tengok di sini the plan and the models. So dia mengikutlah. Model tu try to follow the plan. The estimator try to follow the real data value. Okay, with the best fit 94.6%. Okay, dia punya loss function 0, FPE 0, and AIC negative below 0. So the model is kita boleh conclude di sini dia adalah stable and non-minimum phase. Okay, sebab ada satu zeros di luar. Then we sampling at 50 milliseconds. Okay, so another experiment. So we have a 1,000 samples as well. You divide into 2 for estimation and for validations. Then we obtain the numerical transfer functions B and A. We factorize, simplified, and then we obtain the what do you call that? The pole and zero map. You can see that we have 2 zeros value, minus 1.1 outside unit circle and positive 0.37 inside unit circle. Okay, all poles P1, P2, and P3 are inside the unit circle. So the system is stable and non-minimum phase. You can see that the zero now is catching up to enter the unit circle. Okay, tengok yang pertama tadi. Kat sini kan jauh. Dan yang kedua, bila sampel tinggi sikit, so dia dah dekat. Okay. And then we compare the model output, the measured and simulated. So we obtain 94.54%. Loss function 0, FPE 0, and AIC is below 0, minus 6. Models accepted with a good percentage best fit. Then we higher the sampling rate, 55 milliseconds. Okay, so we captured the data, divide by 2, then we obtain the B polynomial and A polynomial for ARX 331. 331 meaning 3 poles, 2 zeros and 1 time delay. Then you can see that, nampak tak? Zeros minus 0.6 dah masuk dalam unit circle. Zeros yang kedua 0.144 dah masuk dalam unit circles. Okay. All zeros inside unit circles, all poles inside the unit circles. Okay. So meaning that the system now is stable and minimum phase. It's not non-minimum phase anymore. It's the minimum phase now. And the model output percent best fit is 93.22 with the loss function 0, FPE 0, and AIC is 0, minus 6. Okay. So as conclusions, it is true that minimum phase model can be obtained using a large value of sampling time. Non-minimum phase model can be obtained using a small value of sampling time. Okay. So now we go to the MATLAB. Okay. Kita gunakan apa nama ni? Tools yang ada. Okay. But now the technique is different because you are given a data file. So you kena panggil lah open. Nampak tak open sini? Nampak tak open?
Nampak bro.
Open. So data tu kat mana? Data tu dekat desktop kan? Tu ada model A tu. So we just click model A. Okay. So model A dah keluar. Situ model A. So data sama dengan square bracket. Ada 3 kolom situ. Nampak tak? Ada 3 kolom. Okay, kolom yang pertama adalah dia punya index time dia. Kolom yang kedua adalah dia punya apa nama tu? Voltage dia. Yang ketiga ni, ialah dia punya signal input kan, dia punya voltage lah, input signal dia. Dan yang ketiga ni adalah dia punya displacement dia in millimeter. Okay. Jadi kalau kita browse sampai bawah, ada banyak data Ada banyak data ni. 200, 300, 400, 500, 600, 700, 800, 900, 1000, 1100. Okay, so ada 1200. Okay, tutup square bracket. Okay, jadi data dia adalah volt, iaitu input pada kolom yang kedua, 1200 panjangnya. Dan distance-nya adalah sama dengan kolom yang ketiga. Okay, sampling at 45 millisecond. Sampling dia 45 millisecond dan data dia 1200. Okay, Fariha, berapa tempoh eksperimen kita ni untuk model A ni? Dia punya period to capture data berapa? Fariha? Fariha tidur ke? Hello?
Yes, Doctor.
Fariza, Fariha pula. Sorry lah. Salah nama. Okay. Fariza, what is the period of the experiment to capture data for model A? Sampling 45 millisecond, data 1200. Period dia berapa? Multiply lah. 1200 darab 0.045 kan? 54 apa? 54 saat dalam 1 minit lah. Betul tak? Tekan switch tu, tekan switch pada data acquisition tu, sampling on, dia ambil 1200 data. Tengok jari saya ni, macam switch kan? Dia buat 1200 kali dalam masa 54 saat. Tak sampai 1 minit off. Maknanya kita punya data dah dapat lah. Itu yang kita dapat plot tu. Kemudian dah buka data tu, jangan lupa tekan run. Nampak tak run dekat atas ni? Nampak run press run. Okay, nanti dia akan beritahu kat mana path data awak tu. So awak kena beritahu dia lah. Change folder. Jadi dia baca dekat dia baca dekat desktop sekarang. Jadi macam mana nak baca data input, Umar? Data input.
Yes, Prof.
Nak panggil data input macam mana?
Macam mana nak panggil?
Ni VOLT, panggil lah. VOLT.
Oh, panggil vote tu, yes.
Panggil vote. Kau panggil vote, dia baca dah. Bukan? Macam mana nak panggil data output?
Panggil dis tu.
DIST.
Dis. Yes.
Distance. Okay. Nampak? Macam tu. Okay. Lepas tu kita nak panggil GUI macam mana? Nak panggil GUI. Graphic User Interface. ID ENT. Ident.
Ident.
Ignore yang merah tu, tak ada apa. Okay, so sekarang kita sharekan benda ni, takut tak nampak. Okay. Nampak tak?
Nampak, bro.
Okay. Nampak Right. So sekarang kita import lah. Import data tu, time domain data. Bila kita import, so dia keluar satu Windows. Okay. Dia keluar satu Windows. Apa input kita tadi? Umar? Input.
Volt.
VOLT.
VOLT, yes.
Dan output dia distance.
DIST.
Okay. So kita panggil lah dia HYD, hydraulic HYD hydraulic. Starting time dia kosong. Sample time dia berapa, Umar?
0.045.
0.045. Okay. Dan kita letaklah sini adalah input signal dia adalah voltage lah. VOLT voltage. And the output is the displacement. Okay. Unit V, capital V, voltage kan? Capital V bukan small v. Yang outputnya adalah mm. Mm tu apa? Millimeter. Dan kita import. Okey, bila dah import, kita lihat, kita tutup. Okey, dan kita share pada ni. Okey, nampak? Nampak tak HYD tu?
Nampak.
Dan kita ada bawah ni ada time plot, data spectra and frequency function. Press pada time plot. So dia akan berikan plotting yang ni. Nampak? Input output. Atas tu apa?
Output.
Atas output, bawah adalah input Okay. Right. So now kita pergi kepada pre-processing. Okay. Pre-processing. Iaitu kita data dah okey, cuma kita kena buat select range. Okay. Select range. So kita ada 1200 kan? Bagi 2 berapa? Zul? 1200 bagi 2?
600.
600. Estimate untuk 600. Okay. And then lagi 600 seterusnya 601.
Tak nampak, bro.
Oh, tak nampak. Sorry. Tak nampak. Nampak? Tadi saya dah buat dah. Jadi V kan, insert. Okay. Ini adalah select range, pada pre-processing. So now kita ada yang biru ni. Biru ni adalah raw data 1200 yang belum dibahagi dua. Yang hijau adalah dah bagi dua, 600 awal untuk estimation dan merah adalah 600 akhir untuk validation. Next step adalah drag and drop. Estimate pergi pada working data. Okay. Dan validate pergi pada validation data. Drag and drop. So sini adalah E for estimate, ini adalah V for validate. Yang tak ada E, tak ada V adalah raw data daripada eksperimen. Okay. Then kita estimate. Okay, ada banyak models ni. So biasanya kita ambil polynomial model sebab dia adalah ARX. Okay. Di three 331 331. Okay. So kita estimate, okay. So digunakan least square to estimate the parameters. Okay. Oops, terlebih pula. Okay. Jadi terlebih, jadi ini kita buang lah. Terlebih pula tadi.
Kata sampah tu.
Masuk dalam tong sampah. Tong sampah Jadi tong sampah tu dah jadi gemuk lah. Tadi slim kan. Right. So sekarang ni kita nak tengok daripada model output lah. Model output tu adalah kita nak tengok tunjukkan measure dengan simulated. Real dengan estimated. Okay. Nampak? Okay. Daniel? Oh, Daniel.
Ya, saya.
Komen sikit.
So the best fit value for ARX331 model is 92.11, 92.11, and so 331 meaning that 3 poles, 1 for 1 delay time.
Zeros?
3
2 zeros. 2 zeros.
Yes.
Yang tengah tu, 3 tu tolak 1.
Okay. 2 zeros and 1 delay.
So you have a 2 line here, blue line and black line. What does it mean?
So the blue line is the estimated value, while the black line is the actual value from the experiment. So as we can see, the value for the estimated is following closely to the actual value from the experiment.
Correct. Correct. So now, thank you very much. So Daniel, ada lagi satu soalan. What is the ARX331 transfer function? Kat mana kita nak tengok?
ARX331 transfer function, you can double click. I'm sorry.
Double click.
Yes.
Okay, double click. Okay.
And then click to
double click, so kita dapat ni kan?
Yes.
Okay, tu dia polynomial A, polynomial B, 0.045 seconds sampling time, and then the error dia, validation dia. Tu dia.
MSC MFPE 0.0032 and 0.0031.
Jadi plus the percentage tadi, which is 99, tadi berapa 93 94 something.
92.
Macam itulah cara dia. Kemudian satu lagi nak tanya Daniel, nak tengok dia punya mapping. poles and zero mapping kat mana?
Dekat bawah model views ada zeros and poles. Klik zeros and poles.
Okay. Sini.
And then double click the gambar the RX331 again, I think. Ke dah buka?
Okay. Dah buka lah.
No.
Okay.
Yeah.
So macam mana nak keluarkan unit circle?
Oh, itu lupa.
Lupa? Mana boleh lupa? Malam dah cakap. Zoom, disable zoom.
Unit circle.
Disable zoom pada style ni, disable zoom. Dia letak grid. Okay, kemudian letak unit circle. Nampak?
Nampak.
So ada dua zeros, 3 poles kan?
Yes.
System stable, non-minimum phase. Value macam mana value? Daniel?
The value is so the zeros
Klik je.
is in the negative part of the real value at negative something 1.43. Yes.
Lagi satu?
Yes,
Zeros?
and at the positive part of the real value, which is 0.31.
First pole?
The first pole is at the real positive part of real value, which is 0.9995 and 0.372, and one more at the negative part of the value, which is negative 0.46.
Santai. Dah faham lah tu. Okay. Dah boleh lulus lah ni. Dah lulus lah final exam.
InsyaAllah.
Okay. Right. So data B. Okay, saya stop share. Ini pada ni. Data B, saya tak bincang lah. Data B tu lebih kurang sama macam data A. So kita pergi pada data C, boleh? Lepas tu kita nak buat ujian. Chapter 4 ni. Kita buka data C, okey? Setuju?
Baik, bro.
Data B, model B buat sendiri kat rumah nanti. Dia lebih kurang macam model A. Cuma dia punya zero tu dah hampir masuk unit circle. Okey? So kita run. Model C. Then kita panggil data dia, input, volt, dan dist, distance. Okay. Dan kita panggil ident. Okay. Jadi yang ini kita kena apa orang kata? Dah tak nak pakai lagi. So kita delete je lah. No. Okay. No. Kita buka yang baru. Okay. Ident. Okay. Nampak?
Nampak, bro.
Okay. So time domain data. Okay. Input time domain data. Okay. Untuk data C, input dia adalah volt. Outputnya adalah dist. Okay. HYD. Starting 0. Sample time berapa, Zul? Sampling time.
0.045.
055.
055.
Huh? 0.050. 55. 45, 50, 55 kan? Data C tu sample at 55 millisecond. So 0.055 kan? Betul?
Ya, betul.
55
millisecond eh. So voltage, displacement, V, okay. So import. So tengok dia punya time plot. Okay. So atas adalah output, bawah adalah input. Okay. Right. Then we go for pre-processing. Okay, pre-processing, select range. Okay. 1500 dah kita. Nur Fariza, berapa period eksperimen kita? Length data 1500, sampling 55 millisecond.
Hmm, 82.5 second. 83 second.
82.5 second 1500 darab 0.055.
Betul.
82.5 second. Lebih kurang 1 minit 22.5 saat. Betul?
Betul.
Dia longer sikit daripada model A tadi. Okay. Jangan risau, lagi banyak data lagi bagus. Okay. So kita divide by 750, betul? Untuk estimate. Then
Prof ni tak nampak.
oh, tak nampak. Sorry. Dia banyak window MATLAB ni. Nak kena share every window. Nampak 1750 Oh, dah masuk dah tadi. Jadi ni adalah 751 lah. 1000. 1000 pula. 1500. Okay. For V. Alright. Okay. Close. Right. So now, what next? Fariza, what next?
Drag yang height E
Drag,
tu dia
okay.
ke working data.
Then V.
V validation data.
Right. Good. Then go for estimate for polynomial models. You boleh try yang lain-lain lah. Transfer function ke state space ke boleh. So saya fokus on the polynomial models. Okay. So 3, 3, 1. Okay. Then we estimate. Okay. Then we closed. Okay, itu dia. So Fariza, macam mana nak dapatkan measured and simulated output pada satu graph yang sama?
Tekan dekat model output.
Model output. Okay, itu dia model outputnya. Okay, berapa dia punya best fit, Fariza?
Best fit untuk ARX 331 adalah 93.22
Percentage, okay. So
peratus.
black is the real data. Blue is estimated model ARX 331. Right. So kita pergi pada dia punya ni pula, how to get the detail of the model C.
Dan berklik ARX 331.
Klik. Okay. Itu dia. Itu dia A dengan B. Okay. 55 millisecond kan? 0.055 dan kalau kita browse ke bawah, so FPE kosong, MSE kosong. Okay. And then lastly is how to get the mapping. Fariza, mapping.
Tekan dekat 0 and 4.
Activate ni dulu. Activate dulu 331.
activate ARX.
Jadikan dia bold. Bila dia bold, dia aktif. Dia 0 pulse Okey, tu dia dah keluar. Tu dia. So macam mana kita nak keluarkan grid dan unit circle, pergi pada style, disable zoom. Okey, insert grid, insert unit circles. Therefore, nampak tak dia punya dua zeros tu dah masuk dalam unit circles dan 3 poles dah masuk dalam unit circle, dia stable dan minimum phase. And the value adalah dengan menekan pada mouse tu, tunjukkan pada setiap value tu. So dapat nilai dia, atau pakai using calculator. Calculator tu awak factorize lah polinomial B dengan polinomial A. A itu correspond kepada poles dan B itu adalah correspond pada zeros. Alright, kita stop di sini. Okay. Jadi kita akan mula test pukul 3 suku, boleh? Boleh, kita mula pukul 3 suku.
Boleh, Prof.
Sila download cover test hijau tu dengan plagiarism form, print dan sign. Kalau tak ada printer, edit PDF. Dan 3 suku dah boleh start menjawab. Tolong onkan video. Boleh tak? Tolong onkan video. Itu adalah syarat untuk ujian dan exam di UTM. Semua dah ready. Ada soal lagi? Siapa lagi soal? Umar, Zul, Nur Fariza, Daniel, India tu punya?
Yes, Hazim tak ada. Surya, I think dah drop.
Drop Surya dah drop.
Hazim tak sure.
Azim tak sure. Awak kena cekal cekal semangat jangan goyang Lecturer semua bagus-bagus. Dia akan bantu awak. Jadi jangan goyang. Kita hadap je. Ni dia. Sarah Panai. Siapa nama dia budak tu?
Surya.
Sivananta, Surya, Azim. Azim tak ada?
Hazim
tak ada.
dia dah drop.
Azim dah drop.
Hmm.
Dia tak beritahu saya lah. Test tu dah nak mula. Where is Hazim? Sabananta?
I'm here, Doctor.
Ada? Oh, ingat tak ada. Kau ni.
Surya yang tak ada.
Surya tak ada?
Jadi
Surya dengan tu tak ada Okay lah, you can start now. Boleh mula sekarang. On video please. Zul Atfi. On video. Boleh mula sekarang.
Saya guna mobile phone lagi satu untuk audio. Satu video, phone untuk audio.
Tak nampak
Sorry.
awak. Gambar awak tak nampak. Zul Atfi.
Ada untuk satu lagi ni saya ada on video.
Tak nampak.
Ada, Prof. Dia satu lagi, dia ada 2 account dalam ni. Ada 2 nama soal.
Sekejap. Sebab ni semua recorded. Nanti nak MQA, nak buat accreditation. Dia tengok benda-benda macam ni. Kan? Nanti kan tak accredit pula, susah pula awak ni. Tapi tak ada ni, Zul Atfi. Tak ada video dia.
Ada.
3 suku, 4 suku.
Boleh tutup yang sound dulu.
Okey, boleh mula dan kita tamat pada pukul 4.30. 4.30 4.30 tamat. Gate tutup pukul 5. Gate e-learning tutup pukul 5. So setengah jam untuk scan dan PDF hantar. Boleh mula sekarang.
Password Prof tak ada.
Allah, password pula. Oh, sorry. sorry. Password saya pun tak ingat. Kita tengok diary. Banyak sangat password. Dah online ni password dah banyak. Aku pun dah tak ingat. Okey, password dia PW kecil PW 24121. PW 24121. PW 24121. Boleh buka?
Boleh.
Okey, terus start. Okay, masa dah cukup. Please stop writing. Okay. Then please arrange your answer script. The first one is cover. The second one is the plagiarism form and sign. And then your answer script. Together, all documents must be scanned together in PDF. Okay. In PDF and then submit to the e-learning system. So now you have about 30 minit. Lagi 30 minit, get tutup. Okay, so please stop writing and start scanning. So I will end the video and will share the video to you via YouTube link. Thank you very much. So I see you next Saturday for the presentations at 10 a.m. Okay. Thank you.